Welcome to another mathematical moment with the American Mathematical Society. I'm Layla Sloman, and today I'm talking with Anil Ananthaswamy, a science journalist and author of the book Why Machines Learn: The Elegant Math Behind Modern AI. Today we'll be talking about the mathematics behind machine learning models. Welcome, Anil, and thank you for talking with the AMS. For my first question, I thought we'd start off with broad strokes. What is machine learning, and can you give a few examples of different types of machine learning models?
Hi, Leila. Thank you for having me. It's a pleasure to be on your show. I guess, broadly speaking, machine learning is simply the ability of computers to be able to learn about patterns that exist in data without being explicitly programmed to do so. So, for instance, if you are trying to distinguish between two sets of images, one set of images are those of cats and the other set of images are those of dogs, then a machine learning model would be one that would try and discern the kind of patterns that constitute cats and the kind of patterns that constitute dogs. Once it learns what those patterns are, it can then be used to distinguish between, an image of a dog from that of a cat.
Mhm.
So that would be something called discriminative learning, where the machine learning model is trying to distinguish between two classes of data. There are generative models where models learn a probability distribution over data. So, for instance, again, taking the same example of images of cats and dogs, you could train a machine learning model to learn a probability distribution over those images. And then you figure out a way to sample from that probability distribution, and you would generate an image that will look either like that of a cat or a dog, because those were the types of images in your data. So that would be, a generative model. And broadly speaking, most machine learning models kind of fall into these two categories.
Yeah, one thing in your book, you talk about this like very early, extremely simple example of a machine learning model, which is a neural network called the perceptron. Since neural networks are kind of also now one of the most dominant machine learning models, I thought I'd ask you to kind of explain what the perceptron is and walk us through exactly how it worked.
Yeah, so the perceptron was something that was designed by a Cornell University psychologist, Frank Rosenblatt. This was in the late 1950s. And a perceptron essentially is something, it's essentially a computational unit. It is a very, very simple model of a biological neuron. So it has inputs coming in, let's say X1, X2, X3, and then it essentially basically compute something based on those inputs and then decides to classify the output as either -1 or +1.
Mhm.
It's as simple as that. It's essentially trying to figure out uh, whether two sets of data, again, going back to cats and dogs
Mhm.
or circles and triangles, you could have any one of those. As long as these two kinds of data are separated in some mathematical space, such that you can draw a line or a plane or a hyperplane through that through those two clusters, the perceptron will find that hyperplane. And once it finds that hyperplane, then essentially, given a new data point, you can see which side of the hyperplane that data point falls on, and then classify it accordingly, like -1 or +1 or a cat or a dog.
How would, say you have these kind of clusters of data points, how would the perceptron go about figuring out where's the boundary between them or this hyperplane between them?
It's just a very simple algorithm that it's called the perceptron convergence algorithm.
Mhm.
It's something that essentially tries to find a weight vector. Yeah, so the
Mhm.
weight vector is something that is perpendicular to the hyperplane, and it's an algorithm that iteratively tries to make sure that the weight vector has the right value so that each data point falls on the
Mhm.
correct side of the hyperplane.
Mhm.
And it'll do it, it'll try and do that for one data point. it'll move
Hmm.
the hyperplane. And then once it tries to move the hyperplane a little bit closer to the data point in question, it might get other data points wrong. So it iteratively keeps doing this over and over again until it comes to a point where all of the data points classified as, let's say, -1 fall on one side of the hyperplane, and all of the data points classified as +1 will fall on the other side. And once it finds that hyperplane, it stops. Uh,
Hmm.
but as you can see, when you're doing this, it'll just find some hyperplane. It doesn't necessarily find the most optimal one. It'll find, some plane that separates the two clusters, and
Hmm.
then it'll stop. And sometimes these hyperplanes are not optimal.
Right. So, you also mentioned how if the data aren't really linearly separated or separated by a plane, it will be able to find them. So, what kind of changed to go from the perceptron to the neural networks that we use today, which are doing more sophisticated tasks?
Couple of things happened. One was that you had to have many layers, or at least one more layer between the input and output, the so-called hidden layer
Hmm.
of neurons. That was an important step in order to do nonlinear classification. The other thing that was done was each neuron, the once the inputs were, a weighted sum of the inputs was done inside the neuron. In the case of Rosenblatt's neuron, it was essentially a thresholding function. If the weighted sum was greater than some threshold, it would generate -1 or +1. But at some point, people realized that that wasn't enough. The thresholding function had to be something nonlinear. So, for instance, you had to then use something like a sigmoid function to generate the output based on the weighted sum that you had calculated. So
Hmm.
the neuron's activation function itself was modified. And then
Hmm.
also we started having at least one hidden layer in order to find the nonlinear boundary.
Right.
But the big thing that couldn't people knew that this had to be done, but they didn't have the training algorithm necessary to be able to train multi-layer perceptrons or multi-layer neural networks. And that's the change that really happened in the mid 1980s when people like Hinton, Rumelhart, and Williams, when they wrote their 1986 paper on backpropagation, that algorithm was what set the wheels in motion for training multi-layer neural networks.
What do you think is the impact of people learning more about the math behind how these models work?
I think that it's when you look at the math that it becomes clear that um, the kinds of things that these models are doing, whether it's discriminative learning or whether it's learning distributions over data. So when we talk of generative AI, when we say things like, oh, we're generating new data, without really looking at the math, it's really hard to know what one even means by saying,
Hmm.
oh, an AI is generating data that looks like the data that it was trained on. But the
Hmm.
moment you look at the math, it becomes very clear that what it is learning is a probability distribution over data,
Hmm.
and then the math tells you how to sample from that distribution. And when you sample
Hmm.
from that distribution, you get data that looks like what you had given it during
Right.
training, right? So a
Hmm.
lot of these things start becoming more and more obvious,
Hmm.
and so you start appreciating the strength or the power of these models, but
Hmm.
B, also the limitations, because there are certain things that these models will never be able to do as
Hmm.
currently designed, right?
Hmm.
And that becomes clear when you look at the math. So I think both to appreciate the power and the limitations of machine learning models, I think understanding the math is really
Hmm.
important. For instance, large language models right now, right?
Hmm.
If you look at what they're doing, they essentially are again learning probability distribution over
Hmm.
words.
Right.
And so when you have learned the statistical structure of language, and when you give a large language model some input, let's say 100 words, it is
Hmm.
essentially then calculating a conditional probability distribution over those 100 words, or over its
Hmm.
entire vocabulary, conditioned on
Right.
those 100 words, picking the
Hmm.
next word, most likely next word, attaching it to the 100 words, and then generating the next word, and
Hmm.
so on and so on and so on. When you look at it in these mathematical terms, it kind of becomes clear that it's actually not doing reasoning.
Hmm.
Even though the net effect might be that it looks like reasoning, and it is entirely possible that a lot of reasoning, even the kind of reasoning that we do, may involve, you know, sort of next word prediction. But
Hmm.
the real sophisticated reasoning that humans do, which involves compositionality and
Hmm.
learning abstract concepts from one problem domain and then applying it to a completely different problem domain,
Hmm.
um, that is not something large language models are able to do. They
Hmm.
also don't, because you learn a probability distribution over your training data. If your test data is picked from a different distribution, if it comes from so-called out of distribution data,
Hmm.
then it won't work. And
Hmm.
and again, that becomes very clear when you look at the math why it won't work, because it's learned something based on the data that you gave it,
Hmm.
and it has learned a certain probability distribution over in your training data. And if now you're testing it using data that came from a completely different distribution, you don't all bets are off as to what it will do.